said, signal to interference ratio will be determining the performance of the wireless cellular system. And this is the trade-off what I said, right? How the higher value of co-channel reuse ratio is good in reducing the co-channel interference. And what is the trade-off? Means higher the value of n, I say the cluster size will be more, and I will be getting less number of RF carriers per cell. With that, the system will be able to handle less traffic. So, which is not the desired one, right? If I have a lower value of co-channel reuse ratio, the thing is that leads to higher co-channel interference, but there will be increase in the system handling capacity. So selection of the co-channel reuse ratio, I said, plays an important role in the design of the wireless communication system, especially wireless cellular system. So I talked about co-channel interference. That is, how do we define that? It is the ratio of desired signal to the interfering signal, right? And I said with the cluster size of 7 in the first tier, how many interfering cells will be there with the desired signal. So if the desired signal to be at the center cell, then I will be getting 6 interfering co-channel cells. So how it is related and all I discussed it. Okay, then I told about the sectoring, how I can enhance the capacity by using sectoring, right? There are the two ways to do. One is 60-degree sectoring, another one is 120-degree sectoring. So I said with 60-degree and 120-degree sectoring. With 120-degree sectoring, I said only 2 co-channel cells will be interfering with the center cell. So with the 60-degree sectoring, only 1 co-channel cell will be interfering with the center cell. So with that, I can say what is the improvement in the SIR, right? So with the omnidirectional antennas, the signal to interference ratio has been 17 dB. With 120-degree sectoring, it has been improved to 24.2 dB. So as the SIR improves, I can say the system capacity will also increase. Okay, so this is what I discussed in the last class. So let me start today about the channel. Okay, so today topic will be about the broadband wireless channel. I will be discussing about the path loss and as well as shadowing. Okay, so here we all know this wireless communication system, right? So modeling of a channel is an important uh, task, what I can say. So we need to understand how the channel behaves, this wireless channel behaves, because it is very complex and it is not just a free space, okay? Because we need to consider the terrestrial environment. Okay, when I say terrestrial environment, so many things will be there between the transmitter and the receiver, right? So trees will be there, hills will be there, big buildings will be there. So with that, what will be the received signal strength? How do we model that, right? So here, just for understanding, what we consider is the channel is in discrete time. So I can express channel in discrete time as a simple tap delay line. Okay, in short, we say it is TDL. And since it is a time varying, I can write the expression for the impulse response, okay, of the channel as h of k comma t, which is equal to since it takes different paths, right, from transmitter to receiver. So I hope you will be able to visualize a box which is a channel. I can consider that as a system. Input is the data, output is y of t. Okay, so here I have written that impulse response. Okay, h naught in del of k comma t plus h1 in del of k minus 1 comma t and so on. So as I said, since this discrete time channel is a time varying, means it varies with respect to time. Output of the channel will be what? Even if we consider a simple system, if x of t is the input to the system, and if it is an LTI system, right, having an impulse response h of t. So we used to write output of the system as what? Y of t is equal to x of t convolved with h of t. In the same way I have written here. So y of k comma t is equal to h of k comma t convolved with x of k, where x of k is the input sequence. Okay, and h of k comma t is the impulse response of the time varying channel, and y of k comma t is the output of that channel. Okay, so I said here x of k is an input sequence of a data symbol with rate which is 1 by t, where t is the symbol duration. So I can write h of t is equal to h naught of t plus h1 of t and so on, hv of t to the transpose. Okay, so I simplified these things. I have not written with again summation and all. So with the basic understanding of your signals and systems and DSP, I hope you all understand. If the input is x of t, if I have a system, right, if it is impulse response is h of t, then I can write output of our system as y of t. So that y of t will be equal to x of t converted with h of t. That only I wrote here. So here the question is, I have just taken three questions to understand why should I study this broadband wireless channel uh, and other effects like path loss and shadowing and so many other things are there. Okay, so the first thing is, what is the value for the total received power? Means here I said na h naught, h1 and so on, right? Or in other words, what I can say, what are the relative values of hi terms? So hi is the channel gain, what we can say, h suffix I. Okay, I can be, it may take n pause, so I can say I is equal to 1 to n. So what are the values of that hi? Okay, so for that, means how do I determine the values of hi is, so as I said, a number of different effects will cause the received power to vary. Okay, over long long distances, that we call as a path loss, maybe medium, that we call as a shadowing, and for short distance, okay, that we call as a fading. I hope now you will be able to understand these path loss, shadowing and fading terms. Okay, so what is the effect on the received power? Okay, I said there will be number of different effects causes the received power to vary. Okay, the received signal will vary because of a number of reasons. Okay, so one is, over long distance we call that as a path loss. I will tell that what is that path loss and all. Then if I consider for a medium distance, that we call as a shadowing, and for short distance we call as a fading. So because of these things, there will be fluctuations or variations in the signal power at the receiver. Okay, fine. Okay, and the second thing is, uh, how quickly does the channel change the parameter with respect to time? Okay, uh, so the channel, when I'm saying how fast, okay, how fast uh, the channel parameters will change with respect to time, right? So for that, there is a term called channel coherence time. Okay, channel coherence time. So that will specify the period of time over which the channel value is correlated. Okay, so hope you're understanding what I'm saying. Yeah, as we go further, we will be able to understand in detail. Just it is an introductory. What I'm saying, how do, means what are the relative values of hi said, right? So that depends on, I said hi is the gain of the channels, right? That depends on different because as I said, the received power varies due to different effects. So that may be due to path loss or shadowing or fading, right? So for what distances, I call the different names also, I said. If it is for long distance, I call it a path loss. For medium distance, I call it as a shadowing. For short distance, I call it as a fading. The second thing is, as I asked how quickly the channel change with respect to time, right? So that we specify by a channel coherence time. So that will specify the period of time over which the channel value is correlated. Okay, the third next is this coherence time, right? I said it depends on how fast the transmitter and receiver are moving relative to each other. Okay, so it is an important term, coherence time. Okay, so as I said, coherence time specifies the period of time over which the channel value is correlated. I said the coherence time depends on how fast the transmitter and receiver are moving relative to each other. I will show with the example and with the picture also, the next slide. So till that, just try to visualize that. Then the third question is, what is the approximate value of the channel duration? Okay, the channel duration is V here, right? So that value, the channel duration, is known as delay spread. Okay, so if I use the term delay spread, you should understand that it is the channel duration. Okay, and it is measured or approximated based on the propagation distance and as well as environment. Okay, so propagation distance, it may be long or medium or short, and as well as environment, I said. So environment also matters, but whether it is what type of environment we have. Okay, just to understand the first thing, that is path loss, let me take up this. So we consider the free space, right? Propagation, this you all might have studied. What is the uh, Frisch formula? Have you studied anywhere the Frisch formula? Yes, I'm asking you people. Have you studied anywhere about this Frisch formula? Yes. So path loss is a measure of attenuation based only on the distance between the transmitter and the receiver. What I wanted to say is, okay. So free space path loss means what? It is a measure of the attenuation based on only the distance between the transmitter and the receiver. So here I have shown the transmitter. So that is my base station having an antenna. This height of the base station is denoted by HB. Then I have here a receiver. Okay, and its height is HM. Okay, so the distance between this transmitter and receiver I denoted by D. Okay, so you just have a look about this. What I can relate is, so the received power, okay, received power will be equal to what? The gain of the receiving antenna, gain of the transmitting antenna, and the transmitted power divided by 4 pi d by lambda whole square. So I think this you are aware. What is the gain of the receiving antenna and all these things? Fine. I hope you are aware all these things. Yes, students should respond. Are you aware? This Frisch formula you are aware.
Yes, sir.
Ah, so it is basic things. Whatever you people you know, you should say na yes or no. So the free space path loss formula or Frisch formula is this: PR by PT, means this one only I am rewriting. Okay, the received power to the transmitted power is equal to gain of the transmitting antenna, gain of the receiving antenna into lambda by 4 pi d whole square. So this only I rewrote. Okay, so PR by PT is equal to GT into GR to lambda by 4 pi d whole square. So here D is the what? Distance between the transmitter and the receiver, and the lambda is what? Lambda is the wavelength, right? So which is equal to C by F. Hope you understand. Lambda is equal to C by F, right? So what you can understand from this relation? Is it possible to say or interpret something about this? I said lambda is equal to C by F, right? Lambda is equal to C by F. If I substitute that, then what can I say? Yeah, what about the received power? Means I wanted to convey or expect you people to say about how the received power and wavelength or the received power and frequency are related. Is it directly proportional to the wavelength? Can I say it is directly proportional to the wavelength, the received power?
Yes, sir.
Yeah, because the received power, right? PR is equal to PR is proportional to square of the wavelength, I can say, right? Or I can say in terms of frequency, because lambda is equal to C by FC, right? I can say the received power is inversely proportional to 1 by FC square. Fine. So what do you understand by this? Means as the frequency increases, right? As the frequency increases, the received power will be, what happens? See, when it is inversely proportional,
Be less.
will be less, right? So means higher the frequencies, the power means received, power received at the receiver will become less, right? Yes or no? So means there will be more power loss, okay, at higher frequencies than at the lower frequencies. That is what I wanted to convey, right? If I go for higher frequencies, I can say there will be more power loss than at the lower frequencies, right? So that is why the lower frequency band is more in demand compared to the high frequency band. Okay, you all may be knowing, even for this LTE, the 700 megahertz band is fully loaded. Okay, so there is no space only when compared to higher frequencies. Okay, so this is what I wanted to convey. At least hope this is clear. This point, I said path loss is an attenuation which is based only on when the return the receiver. I will come back to this figure. Okay, I will come back to this figure. Hope the slide is changed. Yes, I'm asking. The slide has changed. I gone to next slide. Are you able to find path loss, some other
It's not
equation?
closed.
You're in the same slide.
Yes, sir.
Okay. Yeah. Now.
Now change.
Yeah. Okay. Just I wanted to throw some more information about the path loss. As I said, path loss is the unwanted reduction in the signal strength, right? So during the propagation of the transmitted signal from the transmitter to the receiver. Okay. So why this happens? Okay. So that may be due to many effects, right? Why there will be a reduction in the signal strength, right? As it transmitted from transmitter to receiver. So that may be due to free space loss, refraction, diffraction, reflection, and so many things, right? So I think in this diagram only I have shown. Uh, Hope you are all able to see this diagram. So this is my base station, which I am using the omnidirectional antenna. So these are the different. So this is my receiver. Okay, mobile is there here. So the signal will be reaching from base station through different paths, right? So it is not a free space, right? Because the trees are there, buildings are there, right? So and we say here, see when it is, and it takes the signal takes from base station to the mobile, the different paths, right? So if it is uh, here I have shown the reflection, and here I have shown the diffraction, and here I have shown the scattering and shadowing, right? So these are all the different effects in the wireless channel. I hope you will be able to understand what is reflection. When do we say it is a reflection? When do we say it is a diffraction? When do we say it is shadowing? When do we say it is scattering? Okay. So because I said it is influenced uh, by terrain counters, right? And even about the environment, I was telling about this, whether it is urban, rural, or vegetation and foliage, right? So the propagation medium, whether it is dry or moisture air, right? And the distance between the transmitter and the receiver, and even the height and location of the antennas also. Okay, so because of all those things, there will be reduction in the signal power at the receiver. So there are the reasons I quoted here. Okay, so usually, so as I said in the previous slide about the free space path loss, right? So what is the formula I wrote? PR by PT. is equal to, right? Any one of you can say what I wrote. PR by PT is equal to, yes. Any one of you can say what is the formula I wrote. PR by PT is equal to, means nobody is noting. This is what I understood. When nobody is telling, you people have not noted the expression. See, please note down, na? Otherwise there is no point, right? I told you to note down this equation. This is the expression for free space path loss. This expression PR by PT is equal to GT into GR into lambda by 4 pi d whole square. So this is the free space path loss formula, or we say Frisch formula, right? As I said, GT is the gain of the transmitting antenna, GR is the gain of the receiving antenna, so lambda is the wavelength, and D is the distance between the transmitter and the receiver. Okay. Okay. So I told why the signal is getting there is a why signal is why signal strength is reduced, right? As it propagated from transmitter to the receiver. Reasons I quoted, right? Because of the uh, various effects, right? So usually for a terrestrial propagation, okay, the environment is not a free space, and which is approximated by the two-ray approximation, okay, for the path loss. So two-ray approximation model is the most widely used model for approximating the path loss. So for that, the formula is this one. So either you can tell in terms of PR by PT, or so received power will be equal to the transmitted power into gain of the transmitting antenna, gain of the receiving antenna, then square of the height of the transmitting antenna, then square of the height of the receiving antenna divided by d power 4. So what we understand from this two-ray approximation model is, here the received power is directly proportional to the height of the transmitting and receiving antennas. So height of the transmitting and receiving antenna plays an important role in the propagation. Okay. And the second thing is, here we are not finding lambda, right, in the two-ray approximation model. But in case of Frisch formula, it was directly proportional to the wavelength, right? And what I can say, it is inversely proportional to the carrier frequency. But in this approximation, that lambda is disappeared. Okay. The third thing is, here, see, it is inversely proportional to the distance of what? It is d power 4. Okay, so means the distance dependence has changed to what? D power, that is 1 by d power 4 can be written as d power minus 4, right? So the distance dependence has changed to d power minus 4, means the energy loss is more severe with the distance in a terrestrial systems than in the free space, what I can say. Hope you got my point. The energy loss is more severe with the distance in a terrestrial system than in the free space. Okay, so because it is d power 4, right, the dependence is more. Okay, so this is the two-ray model what I said. Then see, here we use, there are variety of empirical formulas, okay, empirical models which are developed for finding the path loss. Okay, one such model, what I have shown, I said I will come back to this slide. Yeah, now we need to see about the right picture. So this one, is the what the empirical path loss formula. Okay, by considering different propagation environments. Okay, so the empirical path loss formula is this. So PR is equal to the received power is equal to the transmitted power, and then I wrote P naught into D naught by D to the power of alpha. Okay, so where Alpha is the propagation path loss exponent, we say. Alpha is the propagation path loss exponent. And okay, here to say what is D naught and what is D is written here. So D naught, uh, actually the path loss exponent, what I said is the alpha, no? And which is, and this P naught, okay, P naught is the measured path loss, okay, at a reference distance of D naught. Okay, so this P naught is the path loss measured at a distance of D naught. So D naught I have shown here from transmitter to the receiver. So it is at a distance of 1 meter. Usually we consider D naught is equal to 1 meter. So this is considered as a reference path loss, what we can say. Okay, and this is with the actual mobile receiver. So the empirical path loss formula, okay, for the uh, different propagation environment is this. So received power is equal to Pt into P naught to D naught by D to the power of alpha. So to understand this empirical, the means how did they arrive? So they are measuring, either it is measured and they have concluded to this equation. So to understand this, its importance, let me take up one example so that it will be clear how the value of this propagation path loss, okay, and as well as the signal to interference ratio, means how this propagation path loss have an impact on the signal to interference ratio. Okay, so hope you have noted the formulas. One is the Frisch formula is this, and this is the empirical formula, what I said, right? And and this is the two-ray approximation model. Okay. So before I come here, yeah. Yeah, able to read this?
Not clear,
Yes,
sir.
I'm asking able to read this. Huh?
It's not clear, sir.
Full slide ಮಾಡಿದ್ರೆ it is not clear. Okay, I will read. Uh, this is the example. Okay, so consider a user in the downlink of a cellular system. Okay, consider a user in the downlink of a cellular system where the desired base station is at a distance of 500 meters. If I want to tell that 500 meters in terms of kilometer, I can say it is 0.5 kilometer. Okay, and so there are numerous nearby interfering base stations transmitting at the same power level. I hope you will be able to visualize now. So there is one base station, okay, and there is an user, means mobile receiver, and the distance between that mobile user and the base station is of 500 meters. So that much idea you got, that visualization. What I said, there is a base station and there is a mobile user. This, the distance between the mobile user and the base station is of 500 meters. Okay, and in addition to that, as I said, there are uh, other interfering base stations, okay, transmitting at the same power level. Uh, so more than one base station is there near to that, okay, and even other base stations will also be transmitting the power at the same level, right? So here the question is, if there are three interfering base stations, okay, at a distance of 1 kilometer, if there are three interfering base stations at a distance of 1 kilometer, and another thing is, uh, so I said there are three interfering base stations at a distance of 1 kilometer, then three at a distance of 2 kilometer, means at different distances, different number of interfering base stations are there, I'm saying. One, I said there are three interfering base stations at a distance of 1 kilometer, then three interfering base stations at a distance of 2 kilometer, and 10 interfering base stations at a distance of 4 kilometer. Okay, Hope able to get this problem. I said first base station is there, then user is there. The distance between the base station and the user is of how many meters? It is 500 meters. Okay. In addition to that, there are several interfering base stations around the base station of the desired one. Okay. So how many base stations are there at what distance? I'm saying. I said three interfering base stations at a distance of 1 kilometer, then three at a distance of 2 kilometer, then 10 at a distance of 4 kilometer. So three base stations are there at a distance of 1 kilometer. Then another three base stations are there at a distance of 2 kilometer. Then there are 10 base stations at a distance of 4 kilometer. So this three at a distance of 1 kilometer, then another three at a distance of 2 kilometer, then another 10 at a distance of 4 kilometer. They are all transmitting the power at the same level what the desired base station is transmitting. So that is why we call those base stations are interfering base stations. So let us use that empirical path loss formula to find the signal to interference ratio. Okay, that is SIR. So here we are neglecting noise. So take the value of alpha, that is propagation path loss exponent I said na. So which is equal to 3. Okay, when alpha is 3, what is the value of signal to interference ratio? And when alpha is 5, what is the value of signal to interference ratio? Hope that problem is clear. Yes, have you noted that
Yes.
problem what I said? Hello?
Yes, sir.
Yeah.
Yes,
So
sir.
now with that picture, I'm just saying here. So when alpha is equal to 3, I said no, the D naught. Okay. Will be the what? D naught is the what? I said it is a reference distance, right? Which will usually we take that as uh, 1 meter, right? So D naught in units of kilometers. So the desired received power will be, so the received power at a distance of D, okay, so is equal to PT into P naught, right? What is the formula I wrote there? Empirical formula D naught by D to the power of alpha, right? D naught by D to the power of alpha. So the value of D is what 500 meters I said, right? That is the distance between transmitter and the user. So 500 meters. So I have written that in terms of 0.5 kilometers. Okay. So 0.5 to the power of, since I have written 1 by D as D power minus 1. So that is D power minus alpha it becomes. That is why I written here D naught cube into D to the power of minus alpha. Okay. Just substitute alpha as minus alpha as 3. So I will be, this is one expression. Okay. Similarly, I need to find out what is the interference power from that base station. So for that formula is this. So received power with respect to the interfering base stations is transmitted power and this P naught, then D naught cube, right? So here in bracket what I have written is, I said there will be 3 interfering base stations at a distance of 1 kilometer. So that is why, so 3 into 1 to the power of minus 3 I have written. Okay. 3, there are 3 number of interfering base stations at a distance of 1 kilometer. Then next is, there are 3 interfering base stations at a distance of 2 kilometers. That is why plus 3 into 2 power minus 3 are written. Then there are 10 interfering base stations at a distance of 4 kilometers. So that is why 10 into 4 to the power of minus 3. Hope this is clear. Yes, that empirical formula only I am using here for finding the path loss. Hope this is clear, the substitution. D is the what? Distance between the base station and the mobile user, which I said it is 500 meters. So in terms of kilometer, if I want to write, I can write that is a 0.5 kilometer. So which is I substituted here. So that is for the received power at a distance D. Then I am also finding what is the interference power. So for interference power also the formula is same. Only I am finding with a different, what, how many interfering base stations are there at what distance. That is why it is written here. So there are 3 interfering base stations at a distance of 1 kilometer, then 3 interfering base stations at a distance of 2 kilometer, then 10 interfering base stations at a distance of 4 kilometer. So now the signal to interference ratio, how do we compute that? So this is the signal power, right? This is the desired power, equation 2.8, whatever written here, whatever I'm moving the cursor, right? And this one is the interference, right? So the ratio of these two will give you the signal to interference ratio. So with respect to that, if I divide this equation by this equation, this PT, P naught, D naught Q will get cancelled, right? Only 0.5 to the power of minus 3 divided by this will be there. 3 into 1 into to the power of minus 3 plus 3 into 2 to the power of minus 3 plus 10 into 4 to the power of minus 3. So are you able to calculate and say what is the value? It is already done here. It is what we are getting is 2.27. In terms of dB, it will be 3.55 dB. In the same way, you substitute alpha is 5 in these two equations. Okay, you can find out what is the signal to interference ratio. So when alpha is 5, we are finding the signal to interference ratio is 10.32. In terms of dB, it is this much, right? So what we are observing here is, means what I wanted to conclude from this example is, as the uh, propagation path loss exponent is large, okay, then the signal to interference ratio is large, means the signal quality will be good for a large value of uh, what path loss exponent. Okay, so overall system performance can be substantially improved when the path loss is large. Okay, when the path loss is in fact large. Hope this point is clear. So when alpha is 3, what is the value I got? When alpha is 5, what is the value? What we are saying. So this is all about path loss. Yes, at least are you able to understand what is path loss? So it is basically an attenuation of the signal due to distance between the transmitter and the receiver. Hope this much is clear. Yes, my dear student, should say yes or no.
Yes, sir.
So once that understanding is there, what is path loss, then I told 3 equations. One is Frisch formula, right? One is Frisch formula. Here there is the expression for path loss for the free space, and second one I said about the two-ray approximation model. Okay, that is for the terrestrial propagation, so which is actually not a free space. And the third thing is, I said what is the empirical path loss formula. So empirical means by doing experimentation, they have arrived it to this equation. Okay, so for different propagation environments, and I took one example, and I said when the path loss is, when the value of path loss exponent is large, how does it improve the system performance? Okay, so when alpha is equal to 3, what is the value of SIR I said, and when alpha is equal to 5, what is the value of SIR, right? The value of alpha can vary from 3 to 5, okay, especially for urban environments. Okay, so this is all about path loss. So the next thing is shadowing. Okay, so okay, again to repeat, I have taken here how the received power will be additionally influenced by what factors, that is shadowing. So shadowing is basically the propagation of signal through the wall or a door. So that is why here I think with respect to this diagram it is shown. Yes, shadowing, able to understand propagation of the signal through the wall or a door, what you can say, right? So for better understanding, you take this example. When do I say it is shadowing? If the signal is propagating through a wall or a door, then I call it as a shadow. Then refraction, that depends on the density of the medium. Okay, so refraction is, then reflection at large obstacles means big buildings. Okay, then we say the signal is getting reflected. Then scattering, So scattering will happens at small obstacles. Okay. So just it may be a signboard. Okay. So due to that we say the scattering happens. Means here the size of the object is small compared to the wavelength of the signal. That we say the scattering. Okay. So there is a diffraction at edges. Okay. So diffraction will happen at the edges, sharp edges of a building and other things. Hope this is clear. Shadowing. When do we say it is a shadowing? When the signal is propagating through the wall, then we call that as a shadowing. Refraction, then I said reflection with the large objects. Scattering is due to small objects, right? Diffraction will happen at the edges. So there is a standard method for accounting of the variations in the received signal strength. Okay, due to obstacles like trees, buildings, which are located between the transmitter and the receiver. Okay, so that is due to that is introduced as a what random effect that we call as a shadowing. Okay, and the empirical formula for that is this one. So received power is equal to transmitted power. This is power at a distance of d naught, which is equal to 1 meter, right? And this is the a sample of the shadowing random process, that x, then d naught by d to the power of alpha. Okay, so here we model the received power as a random process. Hope this clear. This point, x is a what? Sample of the shadowing random process. So the moment we say shadowing, we consider the random effect. Okay, so the distance trend in the path loss, we can think that uh, as a mean or the expected received power. Okay, so that is in the path loss what we have discussed. And here the shadowing sample, right? That is a random process. That will be the what value that causes the variations from that expected value. So to understand that, here I have given an example. Okay, so this is the distance, x-axis is the distance, and this is the what attenuation. Okay, so this one I call as a path loss. Okay, means I take the mean. We see path loss happens due to distance, right? So I can think that is a mean of the received power. Okay, and over that mean, so there will be fluctuations, right, or perturbations, what I can say. So that I call it as a shadowing. So that is due to shadow fading. Hope this point is clear. I can think the path loss that is due to what distance will be as what mean of the received power. If I take this as a mean of the received power, then the shadowing will be the what variations from that expected value. So that we call as a shadowing effect. So shadowing is caused maybe due to the macroscopic objects, and that has the correlation distance on the order of meters or even tens of meters. And this shadowing is also known as large scale fading. Okay, shadowing is also known as large scale fading. So I think with this I will stop today. Okay, so hope you understood what is shadowing. Yes, my dear student should be able to say, have you understood what is shadowing?
Yes, sir.
Yeah, the propagation of signal through what wall, right? And it is a random effect, right? What is the empirical formula I said? And here we are taking the sample of the shadowing as a random process, right? I give an example by with respect to what I consider the path loss as a distance as the what mean value. From that mean value, the variations of the signal strength will be considered as a shadowing effect. Okay, fine.